Hello friends, welcome to CrackGate CSE, and in this series of computer organization, today we'll be discussing what is floating point data format. So in the previous videos we have discussed what is unsigned data format, how the operation takes place in those format, what is signed data format, what is carry flag or overflow flag, and we have also practiced some question on those data formats, right? So now we are moving on to the floating point data format. So if you have not subscribed the channel, please subscribe the channel and make sure you press the bell icon so that you can get an update whenever I am uploading any new video. Now without wasting time, let's quickly start with this format, right? So first thing that should come in your mind that why we are using this floating point data format. What is the use of floating point data format? So this format is used to represent large and small fraction of data within less memory. So for example, see, there are two values. One is this one value and second is this one. So if you have to store this particular value in the memory, it will take a lot of space, right? So using the floating point data format, we can save or store very large or very small value using less memory, right? So what is the general form of floating point format? So the general form of floating point format is this: plus minus m into b's to the power plus minus e, where plus and minus is signed, we already knew it, and this m is known as mantissa, right? Mantissa, or it is also called as significant or fraction, right? This b is nothing but base. So like in decimal values we are having base as 10, similarly in the binary value we are having the base as 2, right? This exponent is nothing but the power of the base. So we'll be understanding all these things in detail, right? Now general form after normalization. So whenever you are looking at this particular word normalization, so what is the meaning of this normalization? So let me just explain you once. See, like I'm having two values. One is this 1.001 into 2 to the power 3, and another value is 0.1001 into 2 to the power 3. So let's say I'm having these two values and I have to store these two values. So why we are normalizing? Just try to understand with this particular example. Here if you store, you have to store this one, this value and this value. That means everything you need to store. Similarly, if it is 0, you have to store this along with this and this. That means all the things, that means the valid digit or the fraction and the base and exponent, everything you need to store. But we are fixing a parameter so that we can use less memory. So you can say that I am taking the part which is not in fraction as 1. So I am making it implicitly as 1, and we are considering that 1 is a valid digit. We are considering that this 1 is a valid digit. So if this 1 is a valid digit, we are not forced to store this particular value. How? See, whenever we are storing, we will be store this particular value along with this detail. Similarly, if I have to store any such value which consists 0, right? Let me write down here, like value is 1001 into 2 to the power 3. Now if we have to store this particular value, and here you can see we are having 0, so what we have to do over here is we have to make it in such a way that 1 is a valid digit which should come over here. So what we'll be doing, we'll be fixing this decimal point of the point over here. How? It will be 1001 into 2 to the power, this will be 3 minus 1 now, so it will be 1.001 into 2 to the power 2. Now we will be storing only this value and this value, and whenever we are retrieving, we by default consider that we are having a valid digit as 1. So this way the storage of these particular values has been reduced or minimized. So this is the general concept of normalization, right? So the general form after normalization is this. That means this 1 is a valid digit and whatever the fraction part is considered as mantissa. This is base for the binary number, so it is fixed for 2, and this is simple exponents, right? So this is the general form after normalization. Now for normalization, what we do is we do Mantissa alignment. So whatever I showed you right now was the Mantissa alignment, because we was adjusting this fraction amount so that there is a one valid digit in the left hand side and all the fraction in the right hand side. So for example, see here I am having this particular example. Now I have to make sure that this particular value should come in this format, like 1 point Mantissa. So what I will be doing is I will be shifting these value to the right hand side of this point to make sure that it is in this format. So what I will be doing is I will be shifting, like I will be putting this 1.11010111 into 2 to the power 4. Now here you can see that we have shifted how many values? 1, 2, 3, 4. So these 4 values has been shifted to the right. So we'll be adding 4 to it. So what is the final value now? Final value is 1.11010111 into 2 to the power 8. Now you can see that this particular value is in the same format where this is known as Mantissa or fraction, right? Similarly, if you are having value like this, here also we have to make sure that the particular value is in this format. So what we will be doing is we are shifting all these values onto the left hand side, so that we will be shifting it like this. It will be 1.011 and this will be 2 to the power 2. So how many values we have shifted? 1, 2, 3, 4, 5, 6, 7, 8. 8 or 9? Yeah, 8 I think, right? So 1, 2, 3, 4, 5, 6, 7, 8. So I'll be adding 8 over here. Now I think we have to subtract it, right? Yeah. So whenever we are moving the value on the right hand side, we will be adding it. Whenever we are moving the values on the left hand side, we will be subtracting it. So finally it will be 1.011 into 2 to the power minus 6. Right? Now you can see that this is in the same format. So we have to just store these values, not the valid digit, right? Now there are two methods to store a particular value. So data is stored in memory using IEEE formats. So there are two IEEE standards that we are using. According to IEEE standard 754, so we are considering it as 754, and under 754 there are two major formats. So one is single precision, other one is double precision. So the size of the single precision is 32-bit, where 1 is reserved for sign, 8 is reserved for biased exponent. So this BE is nothing but biased exponent. So if you want to note down, you can note it down. So this BE is biased exponent, this M is Mantissa. So 1 bit is reserved for sign, 8 bit is reserved for biased exponent, and 23 bits are reserved for Mantissa for 32-bit. Similarly, for 64-bit format, 1 bit is reserved for sign, 11 for biased exponent, and 52 for Mantissa. So you do not need to be worry about these formats, because I will be taking hypothetical formats so that any format can come. You will be easily able to solve these questions. So I also saw it somewhere that there is one half precision, single precision, double precision, and there can be a case that in exam they will give you a random format like 16-bit format or 20-bit format. Then you have to respond accordingly. So I will be taking some hypothetical formats and I will be explaining you each and everything in detail so that you can handle all kind of formats, right? So now let us discuss each of these one by one. So this S is sign. So sign can be either positive or negative. So we are having a 0 value for positive, for 1 for negative. So if the complete data is in positive, we will be keeping it as 0. If it is negative, we will be keeping it as 1, right? So now move on to the BE, that is biased exponent. So first of all, whenever we have to find out this BE or the biased exponent, that means we are about to store a particular value into the memory, because if we are storing, then only we need to find out this biased exponent, otherwise it is not required, right? So this BE is equals to actual exponent plus bias. In this particular example, 2 to the power is 2, that means the actual exponent is 2. Now what is bias? Bias is nothing but 2 to the power n minus 1, where n is a bit which are reserved for the biased exponent for respective format. So if you are talking about 32-bit format, this n will be 8. If we are talking about 64-bit format, then this will be 11, right? So we can find out the bias. So if we are storing a particular value, we have to find out the biased exponent, and biased exponent is equals to actual exponent plus bias, where actual exponent will be given with the data, and this bias can be found out using the number of bits reserved for the biased exponent, right? And let me tell you one more thing, that so this BE is required when you are storing the data. But what if you have to retrieve the data? So whenever you want to retrieve the data, you have to find out the actual exponent, which can be find it out or calculated using the same formula. So this actual exponent will be equals to bias exponent minus bias, right? So this is very easy. I will be explaining you the examples as well, so do not need to worry about that. Now let me quickly show you few more things, and then we'll be moving on to the questions, right? So now we have find it out what is BE. So whenever we are retrieving the data, we have to find out the sign as well, whether the sign of the exponent is positive or negative. So the sign of the exponent can be preserved using these two conditions. So when BE is greater than bias, when this BE is greater than bias, actual exponent will be positive, and when BE is less than bias, that means actual exponent is negative, right? So now quickly move on to this particular example, and let's try to solve this. And Mantissa is simple, so I'm not discussing Mantissa over here, because we already have discussed that Mantissa is nothing but the fraction part. So this particular format is given. This is a hypothetical format which is having 13 plus 6 is 19 and 20-bit format. So sign bit is 1. For biased exponent, 6-bit are reserved, and for Mantissa 13-bit are reserved. So first of all, we have this data along with us. So how we have to proceed? So first question should be how we have to proceed, what we should have to do at first. So first let me discuss that how you can store the value, right? So first we are discussing how to store the value, and later on we'll be discussing how to read those particular value. So whenever we are storing this value, let me take the format over here. So first of all, you can see that this particular data is positive, so you can clearly mention 0 in the sign place. So it is 1 bit. This work is done. Now you have to move on to the biased exponent. So the formula for the biased exponent is equals to actual exponent plus bias, right? So the actual exponent is 13, right? Now we have to find out the bias. So this bias is equals to 2 to the power n minus 1 minus 1. So what is this 2 to the power n? This n will be 6, that means 2 to the power 6 minus 1 minus 1. So if you find it out, it will be equals to 31, right? So if you write down this 31 in the binary format, it will be equals to 0 1 1 1 1 1, right? Now what we have to do, we have to find out the biased exponent. What is AE? AE is this 13. And how we can write down the 13? 13 can be written as 1 0 1 1 1 0 1, right? So this is 13, 8 4 12 plus 1 13, but here we are having 6. So if it is a actual data, not a fraction data, then we can pad 0 at the left hand side at the MSB place, and if it is a fraction, we can pad the value zeros at the right hand side, right? So now this is actual exponent. We have to add bias value. So the bias value is 0 1 1 1 1 1. So just add these values. This 1 and 1 will be 0 with 1 carry. 1 and 1 will be 0 with 1 carry. This 1 1 1 is 3, that means 1 is here, 1 is here. Again this is 3, 1 is here, 1 is here, 1 and 1 is 0, and this is 1. So this is our actual biased exponent. So this particular value will be stored over here, 1 0 1 1 0 0. So 6 bits are reserved for this. Now we have to move on to the Mantissa part. So what is the Mantissa part? 0 1 1. Here you can notice one thing, that normalization is not required because you are already having a valid digit in the left hand side, right? So this is already a valid digit, there is no 0, it is already 1, so no need of normalizing. So what we can do, we can directly store this particular value. So this is 0 1 1. Now here we are supposed to have 13 bits. Here I am having 3 bits. So what we can do, we can pad any number of zeros as per the limitation, so that it is completely filled. So I am adding rest 10 zeros and so on, so that the size is 13. So this is 1 bit, this is 6 bit, and this is 13 bit. So this is how you can store the values. Now the next question comes is how to read the value, because if we are storing a value, that means we need to read that particular value in the future. So how to read this particular value? See, this sign is 0, so we got to know that this is a positive value, so no discussion on that. Now we have to move on to the actual exponent. We have to find out the actual exponent. So how we can find out the actual exponent? Actual exponent is equals to biased exponent minus bias, right? Bias exponent minus bias. So what is BE? BE is given. So this is 1 0 1 1 0 0. Now what is the bias value? We can easily find out like this. So this is 0 1 1 1 1 1. So now just subtract these. 2 minus 1 will be 1, 1 minus 1 will be 0, right? Again 2 minus 1 will be 1, and 2 minus 1 will be 1, and this will be 0. So here again 2 minus 1 will be 1, 1 minus 1 will be 0, 1 minus 1 will be 0. So I hope you know how to subtract it, because I already explained in one of my previous video, right? So if you find out, you will be getting this particular value. So if you convert this in decimal, you will be getting 13, right? Now the question is how to find out the sign of the exponent. So to find out the sign of the exponent, we are having these two conditions. So now we have to compare the BE with the bias value. So this is BE and this is bias. So compare these two values, we clearly got an idea that BE is greater than bias. So BE is greater than bias. If this is the case, we know that the actual exponent is positive. So I can say that instead of 13, it is plus 13, right? So 1 is valid digit, so it is already there. We are not storing 1 anywhere. In M part, we will be going to the Mantissa part and we will see what is the details over here. So I will be mentioning like 0, 1, 1 and zeros. So I am not writing it down over here. In 2, base is 2, we already know that, and we have found out the actual exponent. So this is plus 13. So this is how you can store and read the values. So now I will be discussing one more data. So let me take the data. Just take me another pen. Okay. So if the data is plus 1.1011, right? If it is 1.1011 into 2 to the power minus 13. So I am taking negative exponent this time, so that you can have a clear idea how to work with the negative exponent as well. So again, what we have to do, we have to store it first. So just I'm taking out this paper. So to store it, first of all, you need sign. So sign is positive, that means it is 0, no issue with that. So I am talking about the storing first. So if we are storing this particular value, so whenever we are storing, we have to make sure that calculate BE first. BE is nothing but the actual exponent plus bias, right? So actual exponent is how much? Minus 13. Actual exponent is minus 13, and we can easily calculate bias. Bias is same as 31. We have calculated over here. So bias is 31. Now here you can see that this actual exponent is minus 13, and if you have to represent this minus 13 in binary number, you have to find out the 2's complement of positive 13. So how to write down 13? 13 can be written as 1 1 0 1, right? So we are having 6 bits for the bias, so I am taking 6 bits over here. Now you have to find out the 2's complement. How to find out the 2's complement? Keep this 1 as it is and change all the zeros and 1. So this will 1 0 0 1 1, right? So this is the 2's complement of 13. And what is 31? Now I'm just writing out this 31. Let me write down here only. So this 31 is 0 1 1 1 1 1. So if you add these two values, I hope that it is clearly visible to you all, right? So if you add these two values, whatever we will be getting, just let me write down here. This 1 and 1 will be 0, 1 carry. This is 3. So 3 will be here, 1 and 1 will be 0, again 1 0, then 1, then 0. So this will be the addition of actual exponent and bias, and this will be stored over here. So 0 1 0 0 1 0, right? Now we have to store this fraction part. So 1 0 1 1 and 0. We are padding up 0 so that it will be 13. So this is 1 6-bit and 13-bit. Now what if we have to read this particular value? Again, to read this particular value, we have to find out actual exponent, which is BE minus bias. So what is the biased exponent? BE 0 1 0 0 1 0. What is bias? Bias is 0 and all ones. So 0 and all ones. So if you subtract it, what you will be getting? You will be getting 1 1 0 0 1 1. Just you can just subtract it. You can easily do it. So this will be the value. Now if you have to convert it into the decimal. So first of all, what we'll be doing is we will be checking the sign of the actual exponent, so that we would be understanding that whether to complement the data or do not need to complement the data. So here you can clearly see that this is biased exponent and this is bias. So biased exponent is clearly less than the bias. That means the actual exponent is negative. And if actual exponent is negative, you have to complement it. And when you are complementing it, you will be getting the value as 0 0 1 1 0 1. So convert it, this will be 13. That means the actual exponent is minus 13. So now if you have to change this value again into the data, how you can do it? We already know that this is 0, that means there is a positive sign. 1 is implicit, that means valid digit. Then we'll be writing out this fraction, that means 1 0 1 1 into 2 is the base, we already know it, and here we have calculated it is minus 13. So this is how you can store the data and how you can retrieve the data. Now there is one variation that you need to discuss, that I need to discuss so that you can understand the way. So the next thing is, sometime the format is designed using excess bias. So if the format is designed using the excess bias, the bias will be equals to 2 to the power n by 2, right? So just remember these things. If the format is designed using the excess bias, this is how you should calculate the bias, right? Where n is nothing but the number of bits in the BE field. Now let me take another example. So the format is same as 1613, and this time it is given that it is designed using the excess bias, right? So now the data is plus 1.1011 into 2 to the power plus 13. Now again we have to start with the same thing. We know this, what is the sign? So sign is plus, that means it is 0, right? Now we have to find out the biased exponent to store it. So biased exponent is equal to actual exponent plus bias. So actual exponent is what? 13. So 13 can be written as 1101. What is bias? So bias will be calculated like this: 2 is to the power n by 2, and n will be 6. That means 2 is to the power 6 divided by 2, which will be 2 is to the power 5. So 2 is to the power equals to 32. So I'm just converting this 32. Let me write down here so that there will be no confusion. So it will be 2 is to the power 6 by 2, which is nothing but 2 is to the power 5, which is equal to 32. And 32 can be written as this, right? Add these values 101101, right? So this is the BE which will be stored here, 101101. Now we have to store the Mantissa, that means fraction part, that is 1 0 1 1 and zeros, right? So this is 1 bit, 6 bit, 13 bit. So this is how you can store. But how to read it? Again the same case. So whenever we are reading it, we will be finding the actual exponent, which is equals to biased exponent minus bias. Biased exponent is 101101, and bias we know that it is 100000, and if you subtract it, you will be getting 001101. Now find out the sign of the actual exponent. So sign of the actual exponent will be positive, because biased exponent is greater than bias. So biased exponent is greater than bias. So this says that actual exponent is positive. So if it is positive, no need to complement it. This will be 13 plus 13. So if you have to retrieve it, 0 tells that it is a positive sign, 1 is a valid digit. Write down this Mantissa part, 1011 into, we already know that the base is 2 and the power is plus 13. So this is how you can find out, or you can store the data, you can write down the data. In GATE, what kind of question come? In GATE, they might not ask you the complete thing. They give you a particular value, and they will be asking what is the biased exponent bits, what are the fraction bits. So these kind of question came in GATE 2012, I think. I'm not sure about this. So try to practice all the questions on this number system, because it is very important, and hopefully you will be getting around one question from this particular topic. So I hope you found this particular video useful, and in the next video I will be coming up with few more practice questions for you all, so that you can have a good grip on this particular topic. So thank you very much for your time. Keep supporting, keep learning, and have a great day.